The Milky Way is rather bigger than the average galaxy. Astronomers estimate it contains some 200,000 million stars. They orbit the galactic center, among them our own star, the Sun. In isolation, the Milky Way is like a separate universe. But travel away, and it's just one member of a local cluster of galaxies. In turn, these clusters form strands. Like dewdrops on a spider's web, each point of light is a galaxy cluster. Each cluster contains hundreds of thousands of galaxies. Figures become meaningless. This is the structure of the universe. Strands of galactic matter strewn through unimaginable emptiness. The further we travel, the further we return in time. For as we shall see, in astronomy, time and distance are linked. To understand distance is to begin to know the universe. With time running backwards, we're looking at the primeval gas clouds that spawned the stars and the galaxies. We're back 15,000 million years. This compact ball is all there was of the universe. We're in slow motion. These are the moments immediately following the instant when time and space began. The Big Bang. Time is running forward, an explosion from a pinpoint that began everything and continues today, ever expanding. But how do we know this? Astronomers began by learning to measure the universe. From Earth, an observation is made of a nearby star. Then from the opposing side of our solar orbit, a second observation. Between the two, taken 6 months apart in space, the star will appear to jump against more distant objects. The width of the shift gives its distance from Earth. The method is called parallax, but it only works for the stars nearest Earth. Space-age astronomy can measure the cosmos. The European satellite Hipparcos is systematically scanning the heavens. Its data will fix distances as never before, and an exact dating of the age of the universe may well emerge. The colour of stars and the spectra they display tell us much about them. Analysed in a spectroscope, starlight is a fingerprint. Among other things, it reveals temperature. Spectra fall into groupings, categories which relate a star's temperature to its brightness. A yellow star, like our Sun, has a brightness rating of 1. More brilliant stars shine blue, rating 10, or 100, even 1,000. If the temperature of a star is known, then its brightness rating gives its distance. For instance, if we know from its temperature reading that the big star on the left is 100 times brighter than the star on the right, then why do they shine with equal brilliance? The answer is that light diminishes by the square of the distance it travels. So in reality, the big star is 10 times further away than the little star. Again, the method is good only for objects close by. How can the distance of a remote galaxy be measured? The discovery of a type of variable star called a Cepheid offered a solution. A Cepheid is slowly pulsing yellow in the right-hand side of this galaxy. Now, because the Cepheid is bright and distinguishable, its period of variability can be easily measured. From this, astronomers can calculate its true brightness. That gives them its distance, and therefore the rough distance of the galaxy. Here's a Cepheid flashing in a galaxy 16 million light-years away. Pictures from the Hubble Space Telescope. As stars can be fingerprinted and studied, so galaxies yield information through their spectra. The further the black lines in this spectrum move towards red, the clearer the message that the galaxy is retreating. It's called cosmological redshift. As the universe continues to expand, all galaxies are in red retreat. A light beam could travel around Earth 7 times in a second. It could reach the moon and back in 2.5 seconds. From the sun to Earth in just over 8 minutes. Right through the solar system in 5 hours. From the sun to the nearest star, 4 years and 4 months. To the galactic center, 30,000 years. Across the galaxy, 100,000 years. The distance can be expressed in light years. To the next big galaxy, it's 2.5 million light years. To the edge of the known universe, 15 billion light years. In such vastness, miles and kilometers make no sense. Only light years can hint at the distance to the galaxies and the turmoil therein. These pictures of galactic unrest are images from the past. They're from the Rosat X-ray satellite. If they took 1 billion years to reach Rosat, then the turbulence they portray happened 1 billion years ago. Galaxies aren't the serene structures once thought. They bump into one another. Here are two in the process of a gigantic galactic merger. This pair is in a gentler encounter. A computer forecast has them go their separate ways. How they unraveled each other is clear in reverse. A picture from Hubble of galaxies about to meet. It's increasingly accepted that this sort of interaction is an important part of galactic evolution. A galaxy in the constellation of Virgo is seen here as a combined optical and radio image. In the early 90s, its center was probed by Hubble. Hubble revealed a cloud of swirling dust. It surrounded what's probably a black hole. In animation now, this could be the scene. Like water down a plug hole, material is whirling towards an irresistible focus of gravity. Nothing, not even light, can escape. This is a black hole. Black holes may power quasars. Largely a mystery, a quasar is the ultimate concentration of energy. 100 times brighter than a galaxy, yet no bigger than the solar system. Technology, like the COBE microwave satellite, is unlocking the secrets of the universe. When COBE took the temperature of the universe, it picked up the background radiation of the Big Bang. In doing so, it confirmed that there had been a moment when time and space began. More recent measurements in X-ray suggest there'll be a moment when the universe ends. A cosmic contraction finishing in a big crunch.